So today's lecture is the start of binary phase diagrams, which are going to occupy most of the rest of the class, meaning most of the rest of the semester. So this topic is comprehensively treated in De Hoff, but I have some reading in Callister, it's Callister, associated with today's lecture. So I know we just finished something on reacting chemical systems. Please don't fall behind on the reading. Turn to Callister and do that reading as well. Callister is a little bit more wordy than De Hoff, a lot nicer pictures. De Hoff is thorough and sort of august. And Callister is a little bit more like those textbooks from high school with lots of pictures in them. So Callister is a little bit easier to start the topic, and I like some of the examples that Callister gives. So that reading, like with the Denby reading, that reading is posted on Canvas. Right. Okay, so binary phase diagrams. Let's just start by drawing some and talking about their primary features. What are binary phase diagrams? Somebody tell me, what is a binary phase diagram? What is a binary phase diagram?
A phase diagram for a system with two components.
Right, thank you. So it is a phase diagram for a system with two components. And normally it's plotted like this, with temperature on the vertical axis and a mole fraction on the x-axis. So if we have two components, we have x1 and x2, and we know that x1 plus x2 has to be 1 by definition. And so you have two composition variables, but only one of them is independent. And so we normally plot something like this. So the mole fraction of 2 will go from 0 to 1. That means on the left-hand side here, we're talking about pure component 1. And on the right-hand side, we have pure component 2. Okay, so it's a diagram of equilibrium for temperature and composition. Here's a typical thing that you have. You might have a solution phase. So you might have a large region where 1 and 2 mix. And often you'll encounter something like a solubility limit. The solubility limit. And when you hit the solubility limit, you enter a two-phase region. So two-phase regions are often indicated like that with something that we call tie lines. So those horizontal lines are tie lines. And what tie lines do is they connect the two phases that can coexist at equilibrium. So let's make this specific. Let's pretend that this is sugar water, that this is a water and sugar solution. And so pure component 1 is, let's say, water. So let's say water. And pure component 2 is, let's say, sugar. All right. So so what this region here is sugar water. Right? That's where you can dissolve sugar in water, and you often see that the solubility limits increase as you increase temperature. That's because the process of making a solution increases the entropy, increases the mixed upness of the universe. We saw that in the very first lecture. And so as you go to higher temperature, entropy becomes more important. We know that because Gibbs equals H minus TS. So as you go to higher temperature, solution phases tend to broaden. All right. What's the solubility limit? What does that mean? Imagine you're actually making sugar water and you start off with pure water. You start off with pure water and you start adding sugar. You're adding sugar, you're moving to the right on this phase diagram. What does that mean? You hit the solubility limit.
It'll start to precipitate out.
Start to precipitate. So when we hit this composition, we can no longer add any more sugar to the solution. Any sugar that we add in addition will precipitate out as solid. So when that happens, I end up with two phases in coexistence: sugar water and solid sugar. That's the precipitate, the stuff on the right. And as I add more sugar to the system, more and more sugar precipitates out, while the composition of the solution doesn't change. So in this region, the composition of the solution changes continuously with the overall system composition. But in this region, the composition of the solution is fixed, even as the overall system composition can vary, because I have two phases. So that's the meaning of two-phase regions, and the tie lines connect the phases that coexist. Okay, so it's just some basics. So let's do an example here. Let's look at an example. Crystal growth by supersaturation. And this is you ever made rock candy? In fact, I've got a big one in my I'm at home, you know. I've got a big one in my son's room. So I might go take a walk and grab it in a minute. So let's see. He's at school, otherwise he'd get mad at me because I'd be taking his rock candy. Don't worry, I'll put it back. So there's the same phase diagram. Here's X2. We'll call this the sol vent. Keep the solvent on the right, the solute on the, sorry, solvent on the left, solute on the right. And here's temperature. And here's a two-phase region with a solubility limit. And here's what I'm going to do. Has anyone made rock candy? Or do you remember? Somebody tell me, how do you make rock candy? What do you do first? Well, let's do it this way. Start.
You start like with hot syrup.
Hot syrup, good. So let's just get there to hot syrup. Let's start with a room temperature solution. Let's start here. 1. Okay, we're going to start there. And then what we're going to do is we're going to heat up. We normally do this on the stove. So let's see, we're going to heat up. 2. So now we heat it up. And then we're going to add more solute. Add more solute. So what we're going to do is we're going to make it more syrupy, right? We're going to make this more syrupy. We're adding more solute. And then what's the final thing we do? Maybe somebody new who hasn't contributed yet?
You cool it down?
Yeah. We're going to cool down into supersaturation. We're going to cool down into supersaturation. That's step 4. And then what's the final thing we do? We wait for spontaneous crystallization. Okay, I'll be right back. I mean, we're showing you is a large piece of rock candy. And how did we make this, right? We took water and then we made syrup and then we heated it up on the stove and made the thing even syrupier, right, until it was really viscous on the stove. And then we cooled it down and we poured the syrupy solution into not a beaker because we're at home, a glass dish. And then we waited, and over a course of maybe a day, right, this thing grew. And you see lots of little crystallites here. It's hard to see over the camera. And if we were really making rock candy, we would have put some strings in the solution to grow rock candy on strings. That's how you normally see it. But all right, so that's one way to use a binary phase diagram. So let's see, we're gonna move on to do some formalism. I want to stop now and take questions on what we've covered so far. All right. Spontaneous crystallization means you're going to end up with sugar water and the crystal coexisting.
Can we get like the energy from this path? Like if we have the delta H formation? No.
Can you get an energy from this if you have? So can you repeat one more time? If you have something of formation?
Like if I have like the delta H of mix, like mixing the two.
Can you get energy from this? I mean, is this it's an exothermic process, crystallization.
Okay.
So this was an instant hot pack. Right. This was the instant hot pack. Right. This whole class just comes back to that thing we did on day 1 with the hot and cold pack. So this is an instant hot pack situation. You have spontaneous exothermic process. Right. It's driven by enthalpy, not by entropy. So there is a heat of solidification, and that heat of solidification is not something we worry about so much when we're making rock candy. But if you're growing semiconductor boules or any other solidification process, you care about it quite a lot, and you have to engineer that. Any other questions on these? This is basics. This is introducing binary phase diagrams through, I think, a very, very gentle example. Of course, they're going to get a lot hairier than this, but I want to make sure people have seen these basic concepts of solutions, two-phase regions, tie lines, and how we can think about processing. Okay, I'll move on. So naturally, because this is thermo, a lot of what we're going to do boils down to bookkeeping. So what we're going to do now is establish some necessary conventions. All right. Let me pause for a minute and call something out. And I hope I remember to do this again at the end of class. In the first class, I mentioned that we were going to be using the software Thermocalc. And so that starts on the PSET that's released today. So if you haven't yet, please do go either look at the course info document or just go directly to the Thermocalc website and download and install their educational version for students. It's free. In our experience, every year there's maybe 1 or 2 students that have a little bit of trouble installing it. That's always been with Macs, but almost everybody, including people with Macs, are able to get this running. In fact, I actually don't know anybody who wasn't able to get it running, which is to say it's a fairly well-designed software installation process, because normally, there's always problems. So get this running on your computer, before you need it on the PSET, which you do it today or tomorrow. It should take 5 or 8 minutes at most. It's not a huge program. Educational version of ThermoCalc. All right, now back to regularly scheduled programming. So now we're going to consider the process of making solutions. And we're going to do this really generically. We have some component A. It has a volume. We're going to spend time on notation here, because the notation, when we're making solutions, it gets hairy, because we have mixtures and we have components and we have reference phases and everything like this. So it becomes really, again, it's all about the bookkeeping. So here we have some volume of A, component A. It has a volume, it has an entropy, it has a Gibbs free energy, so forth. The subscripts label component. So maybe it's water, for instance. Maybe that's water. The dash reminds you that it's an extensive quantity. So that's not volume per mole or entropy per mole or Gibbs per mole. It's volume, entropy, and Gibbs. And the circle is going to remind you that it's a reference state, which when you're making solutions means the pure phase, the pure state. So we have pure A. And we're going to do something similar with B. So we have a container of B. It has its own volume, its own entropy, its own Gibbs free energy, and so on. And now we're going to mix them. And you get something which is new, right? You don't get A, you don't get B, you get A plus B. Let's do some bookkeeping. We're going to introduce quantities of mixing. Quantities of mixing. So let's see. The volume of the mixed system. We're going to set it up this way. It's the volume of A plus the volume of B in their reference states plus something we're going to call the volume of mixing. This is free. We can do this, right? This is no problem. This doesn't tell you anything about the science. This is just a bookkeeping scheme. I see now the top of my screen is Sarah, Josh, and Eli. So let's say that I want to say the amount of money Eli has in his pocket right now is the amount of money that Sarah has in her pocket, plus the amount of money that Josh has in his pocket, plus the difference, which doesn't tell you anything about how much money you have in your pockets. It's just a bookkeeping scheme. That's all this is, okay? So we're going to do something similar with all of the other extensive quantities.
Could the delta V mixture value be a negative number?
It can be. It can be. Sure. What's an example of when it's a negative number? I got to think about this.
And like maybe like water and acids, they usually shrink when you mix them. It gets smaller than it was.
Well, I love the example, but I didn't quite hear what exactly was it that shrinks when you mix them?
It's like water and acid, like
Oh, water and
10
acid.
milli.
Yeah, sure. That's, or sometimes it's larger, sometimes it's smaller. You shouldn't think that, oh, it should be bigger because we mixed it, so the system got bigger. It's, you know, it's a volume of A plus a volume of B plus, however it changed. So if there's chemical interactions that cause the molecules to pull more closely together than they do when they're unmixed, then that volume term is negative. If there are chemical interactions that cause the thing to swell, right? That's the case with like glass formers. Then that becomes positive. Okay, so let me just make this clear. We have this sort of structure here. These are the reference states of pure components. And these are the mixing terms. And the point of having these mixing terms is because when you make solutions, the whole is not simply the sum of the parts. That's why we have these mixing terms. All right, so these new. There are solutions all around us. So there are solutions all around us. We know this, right? Liquid phase, this is where we started. And when people colloquially say solutions, normally they mean a liquid phase. So ocean water, syrup, right? Gasoline, etc. All right. Gas phase, of course. Air is a solution. But in material science, in MSc, we spend most of our professional lives working on solid phase solutions. So this is less colloquial, right? Normally, I think you stop somebody on the street and hold up a solid chunk of something and say, is this a solution? And they would say, no, it's a solid. But everything we're doing applies, you know, definitely to solids, and that's actually where we get most of our technological impact. So would somebody like to name for me some solid phases that matter to you or everyday life or cool extreme examples or anything at all?
Maybe carbon steel.
Steel. Right, the most basic steel is carbon steel. It's iron and carbon. Right? Iron is very, very soft, ductile, rusts easily, not good for structure. Right? You add a little bit of carbon and you get steel. Good. Other metal alloys, right? This is sort of, if you go back millennia, this is where material science started, right? Brass, right? Bronze. These are kind of old-fashioned metal alloys. Even though steel, there's nothing old-fashioned about it as practiced today. We also have super alloys. So now we're getting really into, you know, late 20th century stuff. So for example, cutting edge materials research enables things like jet turbine blades, right? Right? How can you have those big turbofans in modern jet engines? They're withstanding enormous stresses and heat. The bigger you make them, the more efficient the engine becomes. But in order to make them big, you need a material that can withstand that. And so these superalloys are developed for that application. What else? What about lithium ion battery electrodes? Nobel Prize in chemistry from 2 years ago for lithium ion battery development. Largely, almost 80% of the work and intellectual input on alloy design, that is designing solid phase solutions for those electrodes. Semiconductors. Semiconductors, pure silicon with nothing added is useless. It doesn't do anything for us. Right? We alloy it. We make solid phase solutions to change its properties and enable electronic circuits. Any other examples? This is enough, I think, but this is material science. You take something, you add a little bit of something else, and you dramatically change the properties, make it more useful. So, okay. Let's take 3 minutes to talk about solutions and reactions. Why? Because we just finished reactions, and because many of you have worked with reactions in introductory chemistry classes. So you're used to something like this. Take two components, they react to make a third. What's the difference? This is a discrete process. A discrete process with fixed reactants and products. What do I mean by that? Let's say we have carbon and oxygen reacting to make CO2. We're okay with that, right? We don't also have to consider carbon plus O0.71, just choosing a random number of moles of oxygen, reacting to make some molecule that's CO 0.71. Because on the molecular level, there's no such thing as 0.71 of an atom. So we don't worry about composition being a continuous variable when we're dealing with reactions. Why? Because the individual chemical components are discrete, and they undergo substantial atomic scale changes. So really there's some bonding going on, right? Bonds made and broken. And we're going to contrast this with solutions. Solutions, we talk about this, A sub x plus B sub 1 minus x, forming a solution, A of x, B 1 minus x. This is a continuous process. Right. And this is sort of a qualitative thing, but you can say that the individual molecular components remain recognizable on atomic scale. So I'm not going to say too much more about solutions versus reactions until we work on reacting solid gas systems in a couple weeks. But I do want to stop and point this out because we just did reactions. And everything I'm about to tell you in the next couple weeks could be analyzed using the mechanism of reactions, but it would be inconvenient to do so. Just as everything which we did in the last two lectures could have been done using the formalism of solutions, but it would have been inconvenient to do so. So we're doing solution modeling because it's a convenient way to treat systems that are solutions. Right? Nature doesn't care. Nature doesn't care how I write this down, what I call it. So it's just about formalism and choosing the right formalism to make our lives easier. All right, let's move on. Let's talk about solution modeling. This is basically a postulate. This is about making a postulate. So we know that to make predictions, right? We're in the prediction business, right? For intellectual, right? Intellectual growth and profit, right? To make predictions, we need thermodynamic data, right? You can't solve any problems if you don't have data. You need the data. And you know, when we were doing reacting systems, you had carbon and oxygen and CO2 and other molecules, and you could say, "Oh, I know what that is. I've seen that before. I know how to search for that data, right? Maybe I'll just find it on Wikipedia." That's a well-defined thing, oxygen, right? It's a well-defined thing, carbon dioxide, no problem. But every material is different. Every material is different. So for example, if we have, right, database, here's my database, right? Imagine a big cloud database. And here's the entry for carbon monoxide. And here's the entry for carbon dioxide, right? And they each have their own properties, right? You wouldn't assume that you can use something for CO2 and apply it to CO. It's a different substance. All right, every material is different. Does this mean we need a separate database entry for every possible composition? All right, so this is sort of a motivating question. Let's say we have silicon, and let's say like Professor Fitzgerald did when he developed strained silicon, which is now in every transistor below the 40 nanometer node, he started alloying it with germanium. And he added a little more germanium. And maybe add a little more. And I'm just putting a 1 at, you know, the 4th decimal point. I could put it at the 10th decimal point. The question is, do I need a separate database entry for each and every one of these compositions? For every possible composition, no matter how minutely I change it? Do I need a separate database entry as I do for molecular systems? Right? We hope not. We hope not. So we postulate not, right? Postulate that we don't. We're not guaranteed it's going to work, but we do the following. We do the following. We try to model trends in thermodynamics with composition. We try to model trends, right? This is about modeling. Modeling is another very important aspect of the shadow curriculum in O2O. The shadow curriculum meaning things which are essential to being a professional scientist and engineer, but most of you won't take a separate class in, right? So like accessing and manipulating data, basic statistics, plotting, communication, we do explicitly tie in. Modeling's up there, right? How do we model? What is that? What does it mean to model a physical system? We're going to model trends in composition. I think you sort of know what modeling is. Like, let's say you have data and you have some control parameter. That's the abscissa. And you have observations, right? And you go to the lab and you measure that, right? And you each one of these measurements cost money. Let's not make this that your students. Let's make this that you're working at a company, and each time you want to run a test, you have to spend some money, and you have a boss, and that boss they don't want to spend any more money, and you have to make a decision about what's going to be the value for that composition set, right? How do you do it? Do you spend more of your boss's money? No, Sarah says no, don't spend more of my boss's money, right? You know what to do. You say, well, I'm going to postulate that there's an underlying model, and that model has some truth to it, or maybe it's purely empirical, right? Either way, it might have predictive power, and I'm going to curve fit, right? But it's not about curve fitting. It's about postulating the existence of a model and using that model to make a prediction. So you fit the model somehow, and then you say, okay, I haven't done the measurement, but I'm willing to bet that it's a value somewhere over there. And you could be wrong, but you're probably right. Right? We saw an example earlier with the heat capacity, where it was heat capacity versus temperature for cobalt. I don't know if you remember that. And the heat capacity data was like this, and then it had a weird spike during the magnetic transition, and then it went back. So, maybe you missed the spike there. Maybe you get the data wrong. Nature always is full of surprises. But the point is that this works a lot of the time. This type of approach works a lot of the time. And when we're modeling solutions, we call it solution models. Solution models are used in two ways. First of all, we use them to understand atomic scale phenomena. We use it for understanding, and we use it to make predictions. And this is almost always what models are used for in the sciences. When you're taught models, right, like in a physics class, it normally starts from some underlying atomic scale phenomena, and you get F equals ma, and then you build up a model of something, a weight on an inclined plane, and then you can use that to make calculations. And it's not really obvious that you're really generating a prediction engine, right? But once you get towards engineering and you're doing something in the material sciences, and you realize how much experiments cost, right? The economic value of modeling for predictions starts to become a little bit more clear. And it's two sides to this, right? You do it for understanding, and you do it because it's going to let you do something else that matters to you. So let's look at some examples very qualitatively. What about water and ethanol? Water and ethanol, right? Well, these are both polar solvents, and they're totally miscible. What does that mean, totally miscible? Anybody?
Yeah, like in every composition, they always don't separate regardless of composition.
Yeah, that's right. So I'll repeat what Elise said. It means that there's no phase separation. There's no solubility limit. Unlike the sugar water system, these two components will always mix at any composition. So let's say the horizontal axis here is ethanol composition. And I'm going to make the y-axis something which we'll be spending a lot of time with, which is a Gibbs free energy of mixing. And I'm going to put 0 here. So if mixing will happen spontaneously at a given temperature and a given pressure, what that means is that the Gibbs free energy of mixing is strictly negative. Not only that, it also means that the curvature is positive, but we won't mess with that now. Just sort of draw over that there in red to make it a little more clear. So there's my free energy mixing. Now, in the next couple of lectures, we'll start developing functional forms for this, but we're not going to do that now. We're just going to look at this. Unmixed, we have the Gibbs free energy per mole of system equals the Gibbs free energy per mole of pure water plus the mole fraction of water plus the Gibbs free energy per mole of pure ethanol plus the mole fraction of ethanol. That is that's like this. We have the pure stuff, this pure stuff, and this pure stuff before we've mixed it. Right? And then mixed, the Gibbs free energy is that Gibbs free energy before we made the mixture plus delta G of mixing. This is just according to that bookkeeping that we set up. Okay. Right. Delta G of mixing is less than 0, which is equivalent to saying that G mixed is less than G unmixed. Right? The system mixes spontaneously to achieve equilibrium at a fixed temperature and pressure. Okay, so this sort of plot here is not a phase diagram. That's a variable you find in a phase diagram, but that's not. That Gibbs free energy, that's not found in a phase diagram. This is not a phase diagram. This is called a free energy composition diagram. And you will be very, very tired of free energy composition diagrams by the end of the semester. But anyway, that's what it is. It's called the free energy composition diagram. What about water and oil? Right? Polar and non-polar. Well, I'll just go ahead and draw it. You know they don't mix. At least not in the binary system. You can cause them to mix if you add a surfactant. So let's do X of oil. But in the binary, delta G mix at a given temperature and pressure, that's typically what you find. You have a positive delta G of mixing with a negative curvature. And what that means, if the system is initially mixed, it will spontaneously unmix to achieve equilibrium at fixed temperature and pressure. And in the edX version of this class, there's a little bit of a separate demo, a lightboard video, and a demo about the ouzo system, which ouzo is a Greek liquor. It's also known as pastis in French, and it's oil and water, but they're caused to mix with the addition of a surfactant, and so that gets into ternary phase diagrams, which we don't really cover in this class. We don't spend time on it, but it's a fun example. So I encourage you to check that out. All right, so let me just summarize here. Free energy composition diagrams. Free energy composition diagrams are how we draw, visualize, and then evaluate solution models. So they're like the engine room of binary phase diagrams. So we have here something like delta G of mixing. Let's draw this generically. And sort of draw a curve, right? That could be a solution model. This is the x-axis, x of 2. The solution model comes from somewhere. We'll talk about that. And it allows you to make very specific predictions. It allows you to build binary phase diagrams, and we'll talk about that. Right? The solution models, they represent particular phases or I should say structures, like FCC or BCC and so forth, or liquid or gas. And the models are where they're derived from. They're derived from experimental data. They're derived from empirical modeling. Or they're derived from atomistic modeling. So that is, theory. All right. And so this is the core of the class. We're getting there. This is what really enables phase diagrams, which is what enables materials processing. These solution models, we're going to deal with only the most basic ones in this class, and you can go pretty far with that. The basic ones are what they give you in thermocalc. To get the real ones, like if you wanted to get the solution model that corresponds to a superalloy that, say, United Technologies uses for turbine fan blades, you would have to break into a very secure server. Those are databases with enormous economic value. They're trade secrets. Those are not published in the literature. If you go into alloy development, you're going to be doing a PhD, and a lot of that's going to be building solution models. So if you were in the Alinar group or the Tassan group or maybe the Chris Shu group, building these models, these mathematical objects from data and using it to make predictions to design new materials, right? That's sort of the core. That's what's done. So that's the end of the hour. I hope that I've been able to introduce you to the formalism of solution modeling without it being too boring. Because at the end of the day, we're doing bookkeeping, right? And bookkeeping is hard to make. It's obviously important. I think we can all agree on that. It's hard to get too very excited about it, but we have to do it. So I'll remind you, again, thermocalc academic, free software. Please download it, install it well before you start working on this next PSET. The reading for today is in De Hoff and Callister. So do the Callister reading. It's pretty straightforward. There's also an accompanying lightboard video on binary phase diagrams and tie lines in the lever rule. So I encourage you to watch that. You'll find that same content in De Hoff and the same content in Callister, but it's a little more colorful in the video.